In this video, we'll take a look at the MITS, or Micro Instrumentation and Telemetry Systems, Model 1440 Calculator Kit. MITS was a company in the early 70s that started out with various products. Between 1971, they introduced their first calculator kit, which was, I believe, the Model 816. They would release this model, the 1440, in 1973, which is when I acquired one and built this one. They then, around 1974, released a scientific version of this calculator, but by the end of 74 or 75, it was all over for MITS calculators. They would then become much better known for their subsequent product. We're going to go in quite some depth into this calculator. I'll give you a little bit of a tour of how it operates. I'll show you the insides of the calculator. We'll go over the design of some of the circuitry and PCBs. We'll look at some of the original schematics from the manual to show some of the interesting design choices and amusing bugs. And I'll then also talk a little bit about, in fact, a lot about how I had to bring this calculator back to life after 50 years, and unfortunately I had to do it by completely re-engineering it with a new processor and completely new firmware. So let's get started. MITS would, of course, become far better known for what they did after calculator kits, which arrived in 1975 in the form of the MITS Altair 8800 computer, which would go on to become perhaps one of the leading, if not the leading, hobbyist Intel 8080 based microcomputer kit of the latter half of the 1970s and into the 1980s. If you're interested in the MITS Altair 8800 or haven't heard of it, there is a whole Wikipedia article on it and quite a few resources on the web. But before the Altair, there were calculator kits. This ad from Radio Electronics, the April 1973 issue, introduces the MITS 1440 kit calculator, although you could buy it assembled. As I mentioned, I bought mine in kit form. Note the price here was $199.95, which, after I plug it into one of our favorite inflation calculator websites, is the equivalent of about $1,300 in today's money, which even back then was still a lot of money for a calculator. But there weren't a lot of calculators on the market. There were virtually no kit calculators, I remember. Plus this one, as you can see, had a 14-digit display. That was really cool, and especially had square and square root keys. You didn't see that a lot back then. So yeah, and the coupon on the bottom, that's actually how you ordered it. I would have had to send in a check and actually snail mailed it to MITS in Albuquerque, New Mexico, because of course there was no such thing as online ordering or frankly online anything. So this is a cool ad. I'm glad I was able to find it. So the July 1973 issue of Radio Electronics magazine actually had a little article piece on the MITS 1440 kit, because in fact it was one of the first significant desktop calculators you could build from a kit back then. And I brought up this article simply because it's of interest. If you want to read it, you can. It's only 3 pages long. And so here's the other page. Here's sort of a block diagram of the whole thing, sort of, especially of the 6 ICs that make up the main logic of the original calculator. Here's power supply section. I go over this actually in detail in another part of the video. Here's the capacitor board that filters. These are all the capacitor filters on the power supply. They just, for some reason, they decide to show that. And then the last page of the article is here. Shows the display board with the 15 LED digits. This it's a 14-digit calculator. The top digit is just the minus sign, error indication. I actually go through this part of the circuitry in some detail elsewhere in the video. What I find amusing is that they maintained the same error in the schematic. In other words, these lines here that put the cursor, these lines here should not be tied hard, shorted to ground, because if they are, none of the display could ever possibly work. So that's an error in the schematic, and it's just amusing that neither the author of this article nor the original editors of radio electronics caught that just by looking at this schematic. I thought that was funny. So there you go. A quick demo of the MITS 1440 calculator. This is again a 14-digit calculator in fixed point. Couple of things just before I start. The LED display pulsates a little bit here. That's because the LEDs are being multiplexed. However, that's only being picked up by the camera. In the real world, if I'm looking at it myself, they're being multiplexed fast enough that the human eye doesn't see them pulsating at all. They're solid. The other more interesting thing is that you'll notice these displays, although they are 7-segment displays, they're actually made up of 2 dots per segment. And that's kind of interesting because these predate what we now look at 7-segment LED displays, which are made up of little bars. These were a precursor to that. So these are the original displays from the early 70s. So basically a four-banger calculator with squares and square root and a memory function. Right now it's in fixed point mode with 0 decimals showing, and by 0 decimal places I really mean 0 decimal places. So if I do 7 divided by 3, I'll get 2. If I want to see more decimals, I can adjust the number of decimal places that I show, either 1 decimal, 2, 3 decimals, 4, 5, 6, or 7 decimal places. So now if I do something like 355 divided by 113, here's what I get. And again, I can decide how many or how few decimals I want to show. It does maintain all the decimals when it does arithmetic. It's just a matter of how many it decides to show. This has a memory feature, so that if I clear the memory and put this in memory, I can recall it. So if I say 1 plus whatever was in memory, add 1 to 3.14, I get 4.14. Pretty simple stuff. I can clear memory, subtract into memory, add into memory, and to recall whatever's in the memory. There's also a sign key if I want to enter a negative number. So 5 divided by 4, negative 4. So there's 5 divided by negative 4 is negative 1 1/4. 2 other functions, of course, square and square root. Square acts exactly as you would expect it to, and so does square root. Very simple. The last button is the exchange key. This simply reverses the operands. So if I say 2 divided by 1, which normally would give me, well, 2, if I exchange those, it becomes 1 divided by 2, 0.5. So in a nutshell, that's the MITS 1440 calculator. This is the original manual for the MITS 1440 calculator that I saved from half a century ago. As you know, the calculator came in kit form, and so this was the assembly and operation and troubleshooting manuals of a sort. And the actual instructions were, the assembly instructions themselves were not bad. It was the typical step-by-step instructions where you put in a component, check it off, make sure you did the right thing, and it goes on. So in that respect only, it's kind of Heathkit-like, or at least original Heathkit-like. That's good. Picture of the board, where stuff goes, and so forth. Where it fell down certainly was in the area of the schematics. They were basically not terribly useful, although I do go through some of them in this video. but there are some errors. And for some reason, they also put the schematics in the front of the manual before the assembly instructions, and they also put the theory of operation, which is somewhat useful, in the front of the manual. So the theory of operation is actually useful for debugging, and so are the schematics, but in most cases, at least in Heathkit terms, those should come at the end of the manual, not the front. And so that's the Heathkit, the MITS 1440 calculator manual. So here's the MITS 1440 desktop calculator in its original form with the cover removed. You'll notice a few things. One is this calculator was designed on five Countum circuit boards. There's the main board, which you don't see here, except for the mains transformer that's mounted on it. It runs underneath pretty much the whole length of the case up to, but not including the keyboard. It contains the transformer, most of the power supply, but not all of it, and the 6 LSI chips that make up the calculator. And I actually show you this board in more detail elsewhere in the video. Apart from that, there is a filter capacitor board. These have been recapped since originals. I have another section of the video which talks about that. There's obviously the keyboard is a separate PC board with key switches mounted on them. Fortunately, these key switches are entirely mechanical. They're cross-point contact. They're actually fairly easy to take completely apart to clean. And so that's a plus. Not just the keycaps, but I can actually get in and I clean the contacts with some deoxit and had full access. So that's very nice. In addition to that, there's obviously a display LED board which holds the 14 digits plus the extra display, which is used for the minus sign and error conditions. I have a separate section which talks about these particular LED displays. And finally, there's the LED display driver board, which is this board here, which runs about this space and basically runs and multiplexes the LED displays. And that's basically all of the original calculator. This is the capacitor board containing the power supply filter caps for the original MITS 1440 calculator, which if you look elsewhere in the video, I talk about the power supply and the myriad of different negative voltages that it generates, and these are the filter capacitors for each of those sections. The calculator operated fine from the day I bought it and put it together in 1973-ish, and it worked fine for many years. And then eventually it went into the basement, into deep storage, where it stayed until about 10 years ago, where I decided to pull it out of storage after running across it. And before turning it on, I did have a quick look at some of the caps, the original caps, which you see on top. And the two large ones, which by the way are 1500 mics at 16 volts DC, I forget, one of them I remember was not feeling well. It obviously had high leakage or high SR or something. So rather than turn things on and watch them blow up, I thought I'd recap the thing, and so that's what I did, obviously in the bottom on the circuit card itself. But I kept the old caps just to show how, over the years, fortunately, newer capacitors are always smaller than older capacitors. Sometimes quite dramatically so. In this case, not so much, but still. Imagine if it had been the other way around and we had to restore electronics with capacitors that are 5 times the size of the old ones. That would be quite the chore. But fortunately, things have progressed. What's also interesting about this recap job is I don't remember the exact values, I think, of each of these caps, but I do remember that each of the replacements is exactly the same value and voltage rating as the old ones on top. So I thought that was interesting. I was able to source exactly the same components. And after that, the calculator worked for a while and then went back into storage. And after that is the subject of the rest of this video. This is the original main board from the MITS 1440 desk calculator. It's been removed from the calculator and it's sitting on a nice layer of tinfoil because of the PMOS chips on this are, if anything, they're static sensitive. So we want to keep them hopefully running as long as possible. It turns out the power supply's power transformer also sat on top of this board. I'm going to remove it just so it's out of the way a bit. And they're just this calculator was built with designed with a 6-chip calculator chipset from Electronic Arrays, which are PMOS LSI ICs of the time. And it took 6 chips to make this calculator. One of the chips was the input chip. Another one which handled the keyboard. Another one was a control chip which kind of ran everything. There was a program ROM which had the microcode to make the whole thing work. There was an ALU. There's an ALU chip to do the actual math. There's a register chip and an output chip to drive the display. So it took 6 chips to create this calculator back in the early 70s. The only other chip on this card is this thing here, which is, I believe, is a 7400 quad NAND gate being run as an oscillator back to back. So it's basically like 3 inverters with some capacitors and resistors to create an oscillator, and that form the main clock of the entire calculator. A line input fuse, and there's not much else to say about this. The wires, the yellow wires on top here, all went to the display board. The wires on the bottom of this picture all went to the keyboard matrix. Unfortunately, it looks like this board has suffered some corrosion, especially on the bottom right chip here. These chips are actually quite fragile. The white ones, the black ones are plastic. The white ones are ceramic with very thin gold pins, and they're plugged into sockets, which is a good thing. Unfortunately, the sockets have shown some corrosion, and my attempts at gently removing them were not met with success. So rather than attempt to fix it, I thought I'd leave the chips, which I believe work, but have not tested, in this state, and then I can address them at some other time if I want to reinstantiate the calculator as it was. But as you'll see, I decided to leave this board in exactly the state it's in, and basically re-engineer the calculator almost from the ground up, at least from the logic up, and that's what the balance of this video is all about. Shortly after MITS introduced the MITS 1440, which is the subject of this video, not that long afterwards they introduced the MITS 7440, which was a full-fledged, full scientific calculator with full floating point and exponents, as you see here. Same exact case, obviously different keyboard, more keys. A couple of things I wanted to point out, and the reason I bring up the 7440 is to show you the difference, some of the differences inside. From the outside, one of the things you can immediately see is that the LED display is quite different. It's made up of similar 7-segment displays, but these are of course more modern 7-segment displays where each segment is made up of an actual bar or diffused bar rather than individual LED dies. And again, this calculator must have only come out a year or two later, or 3 at the most, after the 1440. What's interesting is if we go look at the inside, and the first thing we see is, whereas the 1440 was made up of 5 circuit boards with the transformer actually sitting on one of the main boards, here the transformer is obviously separate and there's only 2 circuit boards. There's the main board, which includes the keyboard, and as you'll see, the processors, and then there's the LED display board with the displays, sort of like the original 1440 had. If we look at another view of this, again, we're looking from the top, we now see the rest of the power supply except the transformer, which is up here and is nothing but capacitors and bridge rectifier, a diode bridge. And then if we look further from this angle, we see that in fact there's only it's only made up of 2 chips. And this, as for a full scientific calculator, whereas the 1440 needed 6 whole LSI chips just to be a 4-banger with a couple of extra functions. So it's amazing how quickly technology improved in the very few years between the introduction of these two calculators, a handful at most. And at this point, I want to give a shout out to Rick, the curator of the oldcalculatormuseum.com, for permission to use these photos out of his archive. I encourage you also to go visit. It's really interesting. So this is the design of the original MITS 1440 calculator's power supply. Notice this thing generates not one, not two, not three, but four, count them, negative voltages, -8, -26, -14, and -5. Most of these are required by the 6-chip LSI PMOS logic chipset that actually runs the logic of the calculator. And so MITS nevertheless decided to design the entire calculator to run off negative voltages, in particular the -8 volts DC here, which we'll talk about later in the video. Apart from that, this power supply is about the simplest linear power supply design that's Zener regulated you can imagine, with a Zener diode, two filter caps, and the Zener diode's resistor here, and that's it. Plus, of course, the bridge rectifiers. Notice that the -8 is pretty unregulated. In fact, it's totally unregulated. So we'll talk about this later as well. So again, ridiculously simple power supply. I noticed later on that they tacked this 0.01 mic cap here and this 15 ohm half watt resistor here across the AC line. This was an attempt at line, suppressing some line noise if it's present, and that was pretty common in the day. Of course, this being 1972, this C10 0.01 mic cap was not a safety capacitor, which means instead of failing open, if it should fail at all, it may very well fail short or leak, or worse, fail short, which would mean that if that happened, you'd have 117 volts across this 15 ohm half watt resistor, which would instantly draw about 7 or 8 amps, and you would hope that the downstream fuse here, this little half amp fuse, which I looked at it and it was actually a slow blow fuse. So you'd hope that would slow blow fast enough to prevent the 15 ohm resistor from liberating too much of its magic smoke all at once. Who knows? I just thought that was interesting. If I were going to keep this power supply design, which I'm not, I would have probably removed these components, or at the very least replace C10 with an across-the-line safety cap. So that's the design of the original MITS 1440 power supply. As I mentioned earlier, the calculator is made up of 5 circuit boards. 2 of those circuit boards are the LED display boards, which holds all the individual LED digits, which is really one of the things we want to preserve, because that's one of the things that makes this calculator unique, is those very old LED digit technologies. And the other one is, of course, the logic driver and the transistors and all that drive and help multiplex those digits. So I want to take a look at those two, that part of the calculator, which MITS unhelpfully combined into one schematic. So it's very hard to tell which of the components, resistors and transistors, are on the LED board and which are on the LED logic board, but that's okay. When I first looked at this and said, well, how am I going to reuse this section of the calculator? I looked at it, and as I mentioned in the power supply section earlier, it occurred to me, you saw that everything in this calculator is run off of negative voltages. Mostly because of the electronic arrays PMOS calculator chips on the main board. So they decided to make the whole calculator negative voltage driven. So fortunately, there's only one negative voltage which runs the entire display section, and that's -8 volts, which is shown here. It's also shown here. And here, this should be -8 volts. This is an error in the schematics. This is actually -8 volts. And so I looked at this and I said, if I'm going to reuse this, what am I going to do about this -8 volts business? Rubbish, because I don't want to have to design a -8 volt power supply, and then I don't want to have to do level shifting and all that. And then it occurred to me, looking at the schematic, what if everywhere I see -8 volts here and here and here, And here, every time I see negative 8 volts, let's say I just erased that from the schematic and relabeled that ground. And every time I see ground here, here, down here, let's call that 5 volts. And so now, effectively, what I've done is I've reversed I haven't reversed the polarity, but I've basically shifted the whole board's operation up by some volts, so it's all positive. I did reduce the voltage potential to 5 volts instead of 8 volts, but there was nothing I could see in these schematics which would obviously not work if I reverse the voltages that way. And except the IC, but I'll address that in a second, and you'll see how MITS addressed it. So that's what I did. So now the entire display section, the LEDs, the logic is running off of positive 5 volts without any particular ill effect. Looking at the bottom here, this is the 15th LED display, which is not a character, it's not a digit display. It's strictly used to display one of three things. It can display a minus sign if the result is negative, so that the minus sign happens to be the A segment here, and that's only turned on if this sign line is asserted by the calculator's logic through a diode. By the way, these are common anode diodes. The other thing it can display is the letter E, which is the A, F, E, and D segments, and those are only turned on if this error line is asserted. And that happens, of course, if you have like an overflow or divide by 0 or square root of -1 or whatever. That would assert this, and you'd see an error. Lastly, it can display the lowercase letter C, which is the G, E, and D segments. That happens if you turn on this little K switch here. This is the constant switch, which is on top of the calculator and indicates the logic through this output that you want to operate in constant mode, which means, for example, if you're multiplying 2 by 3, you can keep hitting equals, and it'll keep multiplying whatever by 3. And so this also tells the logic, hey, I want to be in constant mode, and it lights up the letter C. If we look at now the top part of the schematic, this is actually driving the 14 digits through the 17447. Now, the 7447, of course, is bog standard TTL. It expects 5 volts at VCC. How did MITS address this? Well, very simply, they took what should have been ground on a 7447, connected that to -8 volts. Because again, this should be -8 on the schematic. VCC, they can't really feed that directly to ground, because then the IC would be the correct polarity, but it would be seeing 8 volts, and a bog standard 7447 or any bog standard TTL would not be, at the very least, not be happy with that, if not fail. So what they did is they put a Zener diode here on a resistor, which ensured that the potential difference between pin 16 and pin 8, between VCC and ground, was not more than the value of the Zener diode, which was about, I believe it was 5.1 volts, which would make sense. So the 7447 is happy. The outputs of the 7447s are the segment drivers, and these go to base resistors and pull-ups, which drive the transistors and in turn drive all the 14 digits as they're multiplexed. And you'll see how that's done in the second half of the schematic. What's amusing about this particular schematic, the way it's drawn, is that it's drawn so it can't possibly work. Because if you'll notice, the outputs of these segment drivers, they're going to the base of the transistors here. That's good, through the resistors. But hey, they're all tied hard to ground. So they couldn't possibly turn on, or I mean, they'd just be stuck at ground, and this would never work. So I think what happened is the drafter of the schematic probably did I don't know, the 1970s equivalent of cut and paste, and he left all these little 7 lines on instead of erasing them. And what's interesting is, if you recall in the radio electronics article that I showed you, it's obvious that the editors of radio electronics, when they printed this article, they redrew this part of the schematic, and you can tell because D6 and D1 have moved around and they're redrawing. So they had to redraw it to make it fit, which is fine, but they didn't catch this error. So it's in the article, it was drawn exactly as shown here. And well, nobody's perfect, but obviously in real life on the circuit board, the segment outputs are not tied all to ground. Moving right along to the second half of the schematic, just as the first half was involved with driving the segments, these drive the digits in the multiplex scheme. There are 14 digits in the calculator. They're labeled D0 through D13, split into two banks. The lower bank is responsible for strobing D0 through D7. The upper bank here will strobe D8 through D13. And so the logic asserts one of these D lines as well as either LHS or UHS here to strobe one digit, and it goes on to the next one. It's a pretty standard multiplexing scheme. Notice again here we have -8 volts in ground, but if you reverse these and make this ground, where this -8 becomes ground, ground becomes 5 volts, everything still works fine, and which is really nice. So that's the portion of the calculator that we're going to preserve, but it was worth going through to see what approach we took. So here's the MITS 1440 calculator opened up with the display board pulled away after all of the re-engineering work's been done. The main logic board is gone, replaced by an Arduino Pro Mini, which you see in the middle of the screen. It's the thing that's covered up in colorful wire and female headers and, well, tape. And off to the bottom of that is an FTDI USB adapter to allow me to program it. This Arduino Pro Mini, if you remove all the wiring and stuff, of course looks like this. This is the one I use. This is one I use for development. It also has female headers soldered onto it, and then the FTDI simply fits onto it to allow programming. The FTDI is of course not required for the thing to actually do its job in the calculator, but I keep it there simply to allow me to reprogram it without having to open up the calculator and plug in. You might note that I could have replaced all of this with an Arduino Nano, which has the built-in USB. I could have done that, and I have Arduino Nanos, but now I used a Pro Mini, and I'll keep it that way since replacing it seems more trouble than it's worth. The Arduino Pro Mini here, its job is to handle the keyboard and to handle all of the math and actual logic of the calculator code. Specifically, it does not handle the display. That's being done by another Arduino Pro Mini, which you've seen on the display board. Let's take a tour of the re-engineered MITS 1440 calculator. We'll start with the power supply. Gone is the original power transformer here. In its place is just a line fuse I installed in a fuse holder. This feeds a barrier strip, which then routes it to the power switch on the cover here and back, and then feeds the input of this 5-volt 3-amp power supply module. The output of the power supply module is 5 volts at 3 amps and goes to the rest of the circuitry. I was originally toying with the idea of reusing the original power transformer and creating a piece of perf board in place of where the capacitor board used to be here, tossing a full wedge bridge rectifier, a 7805, and some of the reused capacitors, and creating a little tiny 5-volt power supply linear, but I decided, I was lazy, so I went on Amazon and bought this 5-volt power supply module rated at 3 amps, which turns out was a bit of overkill because it actually turns out that all of the calculator, even with all the LEDs lit up with 8s, draws just shy of 1 amp when I measured it at the terminals. So the other thing is this power supply actually fits nicely where the capacitor board was, just about the same size, and it mounts decently on the same plastic mounting bosses of the base plate. So it was an easy solution. So a little bit on why I decided to implement this re-engineering of the calculator with two Arduinos, in this case two Arduino Pro Minis. This one here, which is the display driver, the one underneath, which is the keyboard and total logic processor. And there are a number of reasons I decided to do this. It's not so much a code reason. I could have fit all the code on one at AT328, but I ran out of pins. So on the 328 and on the original Arduino, I had just enough pins on this processor to handle the display multiplexing segments and all that, and logic, the I squared C and so forth. I had no pins left. On the processor, basically I also had no pins left after I took care of the keyboard and other housekeeping down there. The two processors talk to each other over I squared C. So you might ask, well, why didn't you just use one more powerful processor with more I/O pins? And the answer is I could have. The obvious thing to do, I guess, using in the same vein would have been an Arduino Mega, which would have had, of course, more than enough I/O pins, and would have replaced all of this. But I decided to split it into two parts for a number of reasons. One is I wanted to keep the display separate. In particular, I wanted to keep the display always running and multiplexing while I was figuring out the logic of the actual logic of the calculator. So I designed the display processor here, this guy, software first. And so it is always multiplexing, regardless of what's going on with the other Arduino, which is doing all the computation and logic and keyboard and so forth. One reason for this was I didn't want to get into a situation where while I was reloading the main processor, the multiplexing would freeze and one of the displays would probably be on at what let's call higher brightness than it should have. One of my main considerations with this display was to run these LEDs at very, very, very conservatively from a duty cycle and current draw point of view. So I didn't want to get into a situation where the LEDs could freeze while I do other stuff and I could only see one display and that would be overdriven, and who knows if that would lead to failure. The display multiplexing code of this thing and the I squared C was simple enough that I didn't have to do much debugging, and it kind of just worked when I started it, and then I left it alone. And there's a little tiny 1 byte command set that I send over I squared C, which tells this guy which digit I want in what position, and it updates itself and just keeps on muxing. And so that's the main reason I split this into two. Plus, I also wanted to experiment. I hadn't done any I squared C between two Arduinos, and so this was an opportunity to make that work and learn about it, and it turns out it's a whole lot simpler than I'd thought. A couple of other things going on here. That's the 7447 I mentioned earlier. This part here, which I didn't talk about earlier, this is basically due to a little daughter board that sticks proud of the board that I had to create, because the quality of these circuit boards from MITS was pretty bad. You basically breathed on the traces and they would lift. And so in repairing this whole thing, I kind of destroyed that area of the circuit board and had to reconstruct it. All this is kind of a it's not really a Darlington pair, but it's kind of a pair of transistors, and all they do is drive all the decimal points, which are muxed for all this. So this is the display decimal point driving transistor. It didn't have to be a Darlington pair. I could have actually done this with just one 2N2222 and called it a day, but I recreated basically what was in the original schematic because, hey, it worked. So that's the display board and display driver circuitry. Let's talk a little bit about 7-segment displays. So here are the typical displays on this 14-digit calculator. You notice each display is made up of dots, not segments, but these are 7-segment displays, similar in concept to, say, the Monsanto Man 1 of the period. You'll notice one thing, though, that the number 6 has a tail on the top. In other words, the A segment is lit for the digit 6. The bog standard 7447, if you know your TTL, actually doesn't generate this tail on the 6, because It doesn't. That's when it was designed in the early 70s, and so neither the 6 nor the 9 have tails. Here's the 9, and I apologize for the quality, but there it is. So the 6 has a top tail, the 9 does not. But the 7447 would generate neither tail. So as you'll see in the schematic elsewhere in the video, there is one steering diode which generates this tail on the 6. And it only does that for the digit 6 when it realizes that it would have otherwise, when it realizes that the 7447 is generating what looks like a lowercase b, it says, aha, in that case I need to turn on the A segment, and so it does. You can't tell here, but the top A segment of the 6s is actually a bit dimmer than the other segments, and you can't really see that here. And again, I apologize for the quality of this video. And the reason for the A segment being a little tiny bit dimmer is that diode introduces one additional drop of current when it has to display that A segment. And so I replaced that diode with a Schottky diode to try and reduce the drop, but it's still a little bit visible. And so that bugged me. But for now, that's what it does. The other thing you'll notice here, there is some flickering in the display. Obviously, the display is muxed. In real life, you can't see that. Or also, the display looks a whole lot better than it does on this video with this camera. So I didn't really like the fact that the tail on the 6 was a tiny little bit dimmer than the rest of the segments on the 6 because of the voltage drop that occurs with the additional diode that steers that A segment on. So I asked myself, well, is there any other way of generating the tail on the 6 than what's being done here? And, well, it turns out there is. Instead of a bog standard 7447, we have the 74247, which is entirely pin compatible with the 7447, except that it generates a tail on the 6. It also generates a tail on the 9, which is less desirable, but we'll see what that looks like. I always wondered, why did they design this chip? Were so many people complaining that 6s didn't have tails when TTL was first invented? So someone said, well, let's do a new one with the tails. I guess so. Anyway, the 74247 is what we're going to drop in and try. The other thing I'll do is I'll remove the steering diode, which would otherwise serve to turn on the 6s. That would no longer be necessary. And that diode actually is nestled right there. You can barely see it. And it's actually, I thought ahead and I actually put in header pins, and the diode is plugged into header pins so I could easily remove it and or put it back as the case may be, depending on whether I like tails or not or what I wanted. So let's put in the 74247 instead, remove that diode, and see what we get. So our new 74247 is in, and the little Schottky diode that I had put in to create the tail on the 6 is gone, because now this 247 is going to do that for us. And it will also generate the tail on the 9 because, well, that's what it does. The original 7447 is over here, along with the stablemates of other TTL that I had removed from over here, which is occasionally curious. It was a JK flip-flop, it was a 7490 counter, and a 7400 gate, and something else. So it wasn't terribly sophisticated, but it did the job of multiplexing the display. Now, of course, the Arduino Pro Mini does that. Let's turn on and see what we get. And again, I apologize for the video. Little self-test starts up. Okay, we have a 0. Let's put in 1, 2, 3. Oh, that actually looks better when I use my hand there. 1, 2, 3, 4, 5, 6, 7, 8, 9, and we see that both the 6 and the 9 have tails without that diode. And trust me, the A segment of the 6 is now the same exact brightness as all the other segments. So success. Do I like the tail on the 9? it's okay. I'll live with it. I had to have the tail on the 6 because without that, it just looked like a lowercase b, and I could have showed you that with the 7447 if I had just removed the diode. But you guys know what that looks like, and that's simply not acceptable. So the 6 really does need a tail. The 9 less so because it's not doesn't look like any other letter without it. It still looks like a 9, but since this 247 creates a tail, we'll leave it at that. And maybe I'll just run the calculator this way for a while. I thought it would be interesting to take a look at the 7-segment dual inline package 14-pin displays that make up the MITS 1440 calculator's overall display. This is one of them. This is actually not one from the calculator. This one was actually a defective one that 50 years ago when I built the kit was defective, and MITS was kind enough to send me a replacement, which has been working fine ever since. So this is the semi-dead one. These are common anodes displays, so common plus if you understand what that means. And one of the anodes is not connected or dead, and so some of the 2 or 3 of the segments don't work on this one. The others happen to work, but the thing is basically useless. I actually had to cut this out of the calculator, I remember, because these are soldered. The kit has you solder these in, and so I didn't have good desoldering equipment back then, and I simply cut this out and soldered a new one in. It was kind of crude, but it works, and it looks fine. So what's interesting about these have to be very early displays, 7-segment dual inline package displays, because there are a few things here. First of all, I don't know if you can see this, each segment is made up of 2 LED dies. And so each segment is made up of 2 little discrete LED dots. That's it. You can see this when you look at the calculator. It looks very retro. I think it looks cool, which is one of the reasons I am restoring this calculator, because of this display. So modern displays, of course, each segment is one big LED diffuse light pipe bar, and that's it. But here we have individual LED dies, 2 of them per segment. Also, you notice the epoxy is not red; it's clear. So the LEDs shine red, of course, but there's no filtering, which is why the calculator has a red filter on its bezel to make it nice and legible, and it looks really nice. There's also, of course, a right-hand decimal point down on the bottom right here. There's no manufacturer here. Nothing. There's no branding at all on this. There's on the back there is some writing, and if we look at it, I've tried to read this over the years. I would like to think it says something like STL 7237, something like that. STI, I don't know. This writing does not come off. It doesn't erase. It's underneath the epoxy coating. So someone hand wrote this before the thing was fully encapsulated. That leads me to believe that these were rather early hand-finished, if not handmade, displays, and MITS got a bunch of them, and they work fine, but as you'll see, they're not at all like current displays. To contrast this, I have a more modern display, well, slightly more modern, not contemporary, but slightly contemporary, but slightly more modern. This one here. So at first glance, looks very similar. Let me see if I can catch the light. There we go. First of all, this is a big M, so this one was made by Monsanto. I don't happen to know the exact Monsanto model number, but I did check the pinouts. This is also a common anode, and it is compatible with it pinout-wise with a TIL 302 display. So a very nice 7-segment display. However, note that in this case, each segment, and I'll try and orient it so you can see it, each segment is made up of 2 bars of LEDs. And each bar, these are not light pipes, these are still individual LEDs, but each bar is made up of something like 4 teeny weeny LED dies. So it looks like little perforations. A different look, also retro, kind of nice. And a red epoxy this time. And on the back, there's also no branding. But you notice this is a Newell stock if you want. I've never installed this anywhere, although I have used it to fool around with. So you might ask, well, if you needed to replace, couldn't you put one of these in? Let's put it upright the right way.
And notice the notches are there to orient you upright, the two notches on top. Couldn't I put this one in? And the answer is no. Why? Very simple. They're both common anode, but the pin outs are entirely different. And if we turn it around with both facing upwards, and I promise you they're both facing upwards here, although you can't see the notches. The pins are very different, are organized differently. If we look at on the one from the MITS, the one that's cut off, start at the top right. There's 2 pins going clockwise. There's 4 pins. There's 2 pins, and there's 3 pins. If we look at this one, starting on the top right, there's 3 pins, 2 pins, 4 pins, and 2 pins. So effectively, they're kind of mirror images of each other in terms of their pin out, which is, I don't know why they did this, makes it interesting. This became more or less the new standard. If you go out and buy a commercially available or new old stock, contemporary display with the ones with a big red, diffuse bars, light pipes, they'll probably have this pin out. So that means that I've never found one with this pin out since, and I've looked. So this now has a status of unobtainium. If I had to replace any more of these on the calculator, what I would have to do would be to design an entirely new display, long little circuit board that holds 15 displays, and create a brand new circuit board to accommodate more modern dual inline displays such as this one or something more modern. The other reason I suspect this was something very new and very unique and probably prototypey when it came out I believe this was MITS's first desktop calculator in 72, 73 that used LED displays. The subsequent ones used, like the 7440, used displays which we consider more common with the bars that make up each segment and with light pipes and so forth. And their earlier one, the 816, or that class, did not use LEDs at all. It used vacuum fluorescent 7-segment displays. So that's why I think this might have been one of the very, very first 7-segment dual inline packaged LED displays.
Because I re-engineered the calculator and actually wrote entirely new firmware to run the whole thing, I thought I'd make a few tiny upgrades. I wanted to keep the operation pretty much exactly the way it was, but bring a couple of functions into the 1990s, if not the 21st century. So now we're running with brand new processor, updated firmware. It actually now does a little self-test, so you can make sure all the displays, segments, decimal points are running, and we start up exactly like we do normally did before with 0. I can still do arithmetic, 2 plus 6, 8, and so forth. I can display as many decimals as I want, so 0, 1, 2, 3, 4, 5, 6, 7, just as the original calculator did. So again, 355 divided by 113 still gives me that. For some reason, the original logic chips, the original PMOS electronic arrays LSI chipset only allowed you to select up to 7 decimal places of fixed point display. And I didn't really understand why that was. I thought there's really no reason you can't go further since I use the number key to figure out with the D key to figure out how many decimals to show. There's no reason I couldn't show more, and so I decided to allow it to show up to 9 decimal places. So a third displays as you would expect, up to 9 decimal places. One other thing I decided to do was I didn't see any reason why this had to be a fixed point calculator, because obviously it can do fractions. So I thought, well, maybe it would be nice if we also allow it to do floating points. So I added the ability to select the D key and the decimal point. So instead of a number of decimals, you select the decimal point. And unlike selecting D0, if you select the D decimal, you're now in floating point mode. So now if I do something like 1 divided by 2, it actually moves the decimal point over and shows me the fraction. In fact, it'll show the answer to the best resolution that it can. So if I again do 355 divided by 113, it'll show me the integer part and then as many decimals as it has leftover room for in the 14-digit display. or I can enter, of course, I can enter a fraction. So 0.2345 times 69, that, square that, and again, the decimal point moves over just like you'd expect in a floating point calculator. Last thing I did was I gave the calculator uh, what Hewlett Packard would call back in the day continuous memory. Originally, of course, if you turn the calculator off, you'd lost the information in the one memory register. I thought, well, why not make that non-volatile so that I can recall it and save it even if the power goes out. So if I can clear the memory is empty. I can put in a number, 355 divided by, so I'll put in pi, and I'll add that to memory, clear, recall memory, still there. If I go and turn the power off and turn it back on, goes this little self-test thing, comes back, but now if I recall memory, there it is. So since obviously the processor I'm using has double EEPROM, I thought why not use it. The other thing, by the way, it saves through a power through losing power is the number of decimals you've selected. So if I select 5 decimals and turn it off and turn it on, the number in the X register will be lost, but not the memory and not the number of decimals. So here's the 5 decimals, and here's the number that was in memory. So apart from that, it works exactly like the calculator did 50 years ago. So as I mentioned before, this re-engineering of the calculator has two processors, both Arduino Pro Minis. One of them is the display processor. This is just a quick look at the code that makes it up. It's not very long. It's deliberately very simple because I wanted to, first of all, I wrote this first, and I wanted to just run, be extremely reliable, and never stop because I never wanted the display to stop multiplexing for reasons I mentioned when I talk about the display. This thing talks to the main processor, the other calculator's main processor over I2C, and basically it implements a little command set here that simply tells it what to display where. So you tell it, in 1 byte commands, you tell it where you want that particular digit to go, and which position you want, where the decimal position to go, whether you want the negative sign on or off, and so on. It's really simple. The other processor is the main display processor. It's quite a bit more complicated. It's rather long. Oh my God, it's about 800 lines of code. It is responsible, as I mentioned, for only two things. It is not responsible for the display. That's the display processor. It talks to the display processor over I2C. The main processor, is responsible for only two things: running the keypad, which was the original MITS 1440s key matrix of buttons, which actually I define here. So they're all here. The rows and columns, and for that I use the standard Arduino keypad.h library because it seems to be working very well. The other library of note that I want to give credit to is a library called bignumber.h. This is an arbitrary precision big number arithmetic, so it'll handle very, very big numbers in floating. It'll handle floating point numbers with lots and lots of digits. I forget what the maximum is, but I'm pretty sure it could handle 100-digit multiplying or doing arithmetic on 100-digit numbers. To give this thing credit where it's due, this is Nick Gammon's big number library for Arduino on GitHub. So that's worth using if you ever want to do arithmetic on very large or heavy, high precision floating point numbers with lots and lots and lots and lots of decimal places. I set up the code, I think, so it does all the arithmetic. It sets this up so it does its arithmetic in like 16 digits worth of precision, and then rounds if it has to just fit it all in the 14-digit display as necessary. the more challenging parts of the code of the main processor, frankly, was twofold. One was normalizing the output of big number to fit into the display and figure out where does a decimal point go, which digit does that go, how in floating point mode, how do I want to move the main the integer part versus the fractional part, which numbers go where on the display. That's actually was a little challenging. And because I designed this first to only support the fixed point mode of the calculator, because that's all the calculator came with originally, I wrote a display routine to do just that, and it's rather long. It's in here somewhere. The later on, I revised the code to add a floating point display mode, and rather than adjust the fixed point display routine, I wrote a brand new routine just to do floating point display, and so it uses one display routine or the other depending on which mode it's in. That was actually a little bit simpler. For some reason, that was a little bit simpler to do, but still fairly challenging to move the digits and decimal point into the right place and optimize the display. And then, of course, there's a logic of the calculator. This is an arithmetic logic. In other words, you do 2 plus 2 equals. And the problem, frankly, if this had been an RPN or reverse Polish notation calculator, life would have been so much simpler because in reverse Polish notation, you put like 2 plus 3 would be 2 enter 3 plus, and plus would simply take the two things off the stack. I wouldn't have to worry about the state of the machine. I wouldn't have to worry, is there a pending operation, or did the guy just hit equals, or what? Nevertheless, so the calculator logic, this is my first attempt at it, and it took me a while to do the proper state machine for it. But it works exactly as it should, and still can handle the x squared and square root keys, as well as memory keys interspersed with arithmetic operations. I didn't put this code up on GitHub or publish it because, frankly, it's of absolutely no use to anyone unless someone A has a MITS 1440 calculator and B is re-engineering it into exactly as I did using a couple of Arduino processors. I estimate the surviving population of MITS 1440 calculators in need of any kind of repair to be in the country to be in the very low single digits, if in fact mine isn't the only example. So in a nutshell, that's some of the thought that went into the coding of this re-engineered calculator. So we're done. I just wanted to give you some closing thoughts on this project, and I thought it would be appropriate to leave up a static picture of the original MITS 1440 main board as it existed and still exists, except it's in deep anti-static storage. I really don't know, whether it's just the corrosion on some pins on the bottom right chip there that prevented it from working again. Or if it's something more. I think it's just corrosion. Could it be cleaned up? Yes, if I was so inclined. But frankly, I wanted to take on the project of re-engineering a calculator, so I thought this was a good opportunity to do so. So the way I look at it is this mainboard with its 6 LSI PMOS is in two states of repair. It's either broken permanently or it's not broken or unrepairable. It's kind of like Schrodinger's cat. So someday perhaps I'll re-examine it. There's nothing I did to the calculator which would preclude me from putting it back the way it was, because I kept all the parts, the transformer, the caps, this board. The display processor board is virtually unmolested. I just have to put some chips back on, and the LED board is exactly as it was, totally untouched. So I could do that. So perhaps someday I'll feel motivated to actually repair this board if it's possible. I'm hopeful it is. On the other hand, what I might be more tempted to do, because I'm not terribly in love with the way the two Arduino Pro Minis, I like the architecture that I came up with, but having them sort of physically arranged as they are within the case and underneath and on top of the display board is not what I I'm terribly proud of. If I were to redo this, I would probably, if I were motivated, I would make a brand new PC display board PCB. I'd keep the LED board exactly the way it was. Create a brand new display board on which I put a couple of ATmega 328s, and basically that's about all it would take. Some connectors for the keyboard, and it would look really spiffy. The reason I'm not doing it is because, frankly, this is the only 1440. It's quite reliable now. It's turned into my daily driver now that it's been re-engineered. It's very reliable, even though it may not look it inside. So I'm kind of lazy. But if I were to, if I wanted to take on a PCB design project, I would probably do that and have the PCB made. And I'd wound up with, if you've ever ordered PCBs from China, you probably know that you get 5 PCBs regardless minimum. And so I'd have one of them in my calculator, and I'd have 4 more that would be absolutely useless to anybody else because I'm not aware of any other 1440s out there. Another thought I had is, as I mentioned many times, I'm running the most valuable thing, apart from the LSI chips in the calculator. The most valuable things these right now are the individual 15 LED displays, the DIP LED displays, because as I mentioned, they are unobtainium. They are unique. They have a unique pinout, as I showed you. If one of them were to fail, well, what I would do is, if it was a digit, I would probably take the 15th LED, which is the sign and error display, and migrate it to that, and then do something, little LEDs just to show the negative sign or something. The other alternative would be to completely redesign a new LED board, but then it would look like every other. I'd put in modern. I'd put in 1990s. I don't know, LED displays, which have those bars, light pipe type displays, which would look like every other LED on the market. And that's no fun because that's not really what this calculator is all about. This calculator is frankly, all about its history and its display and the cute little dots. The closest display that I have quantities of, actually, which would look something like these, would be a TIL 311. Which I'll let you look up if you're interested. But these are basically Texas Instrument individual digits, but they interestingly have, each one has a built-in BCD to hex decoder. So you pump in 4 bits, sorry, and it displays, each individual one displays a number between 0 and F. And it has a built-in latch, but driving them would mean completely redesigning the board, because you can't. They're not multiplexed. They each has individual latches. There'd be power supply considerations. Anyway, my point is, I'm probably going to leave the calculator exactly the way it is. It's running fine. I use it every day. I kind of like it, and I hope you found this informative or entertaining. And thank you for making it all the way to the end. And again, thank you for watching.